Hey, how's it going? Yeah, let me set up and then I'll wait till more students come in, then I'll just pass them out together so I don't have to go in and out. Okay, let's see how we do. Desktop. That's good. Okay. Notes. Okay, great. This, like that. Set up. First.
That's with you.
Yeah, I do.
Often to the side,
I beg your pardon?
often to the side.
Okay. Here you go. Okay. Oh, okay, so, come on up. Please. No,
McCants, MCC.
McCants. Okay, Duncan.
Yep.
Okay. All right. Okay. The lights on. All right. That's not quite what I want. Look that up. Right, let's start with this. Oy, 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 oy. Oh, hot. Oh, hot.
You don't have a third test, do we? Yeah, there's two. Okay.
Okay, let's begin class. So the first thing I'd like to do is I'd like to review the schedule. So today is the 18th of November, and so homework 10 is due. So after today, there's only 2 more homework assignments left. There's homework 11, which is due a week from today, and then there's going to be homework 12, which is due Tuesday, December 8th. Okay, so in total, there'll be 12 homework assignments. I will drop the lowest 2 of your homework scores. So the highest 10 of your scores will be counted for your homework grade. Okay. So the final exam is on Friday, December 11th. I'm still thinking about how the final will be constructed. Basically, you're going to have to take it online, obviously. And so what I'll do is I'll definitely send out a Zoom link beforehand for the final exam.
Oh, really?
And I'll give you more details about the final too, as we get closer to the final. Okay, are there any questions on the schedule leading to the end of the semester? Okay, so starting, so after this Monday, everything goes online, as you're pretty well aware. So I won't be Zooming from this room, probably. I'll probably be Zooming from either my house or my office. Let me remind people that if you haven't done so, please pick up your homework exam. I mean, your midterm exams. So they'll be available today, Friday, and on Monday too to be picked up. Okay, so even if you just stop by and just pick it up, it's fine with me. Okay, you're not forced to stay for class or anything. I'd rather have you come and actually pick up the exams. Okay, questions?
Yeah, I joined, I guess, a bit late. So
Sorry, can you speak up, please, Chris?
yeah, I joined a bit late. So the last few homework sections you highlighted there, that's all one collected homework at once.
Yes, that's correct. So
Okay.
it's just one big homework assignment. It just didn't make sense to divide it up. It just divided up in a very weird way. So, either you can decide if you're doing well in the homework, you can decide to actually turn it in. If you think you really need to help out, I would encourage you to turn it in.
Gotcha.
Okay, but I didn't want to sort of penalize you for not turning it in, because I will drop the lowest 2 homework scores.
Okay.
Okay. Other questions? Okay. So let's go to work. All right, so today we're going to continue on with inner products. So we were talking about inner products. That's the same thing as a dot product. We're going to talk about the idea of length. And later we'll talk about orthogonality. Okay, so these are very important concepts in linear algebra. All right, so let me remind you of the dot product. Okay, so we've seen this several times. So if you take vectors v and w, let's say in Rn, then we have v dot w, and matrix multiplication language, that's v transpose times w. So we're taking the row vector v1 up to vn, and we're taking the matrix multiplication with w1 up to wn. Okay, and so when we take the matrix multiplication, you know, we're basically taking v1 w1, v2 w2, and we're summing everything up. So this is going to be v1 w1, v2 w2 plus vn w1. Okay. And then let me just review the properties. So I actually went over these last time, so this is just a quick review. So first of all, if I take v dot w, this is the same as w dot v. Okay, so the dot product is actually commutative. Two, we have a distributive law. It actually works on the left and on the right. So I'll just state it on the left. So if I add two vectors together, I take the dot product, I can sort of take the dot product of the first thing plus the dot product of the second thing with w. So this is u w plus v w. And 3, if I take a scalar times v w, so c is just a number, then basically you can put the scalar anywhere. So this is going to be equal to c times v dot w. So you can take the dot product first and then multiply by c. Okay, 4. So if I take the dot product of a vector with itself, it's always bigger than or equal to 0. And the dot product of u with itself is equal to 0 if and only if u is equal to 0. So this is a u over here. Okay. All right, so we'll see this, we'll see the reason why in a moment. So if I define, well, let's just first of all look at u dot u. So I'm going to talk about the length. So if I take a vector v and if I dot it with itself, it's going to be v1 squared plus v2 squared plus vn squared. Okay. So if you use the distance formula, so let me draw a picture. Ooh. Okay. And let's say this is my vector v out here. So the length of v, you could just use the distance formula. So the length of v by the distance formula is the square root of v1 squared plus v2 squared plus vn squared. Okay. So if you look at the dot product, it's related because you just take the square root of the dot product. Okay, so length, you take the dot product and you just take the square root. Okay. So what we'll do is we'll call this the length of v. Okay, so you either use a distance formula, equivalently you just look at the square of the dot product. Now, let's say I have two vectors and I want to know the distance between the two. So me draw a picture over here. So I have V and I have W, okay? So if I want to know the distance between V and W, well, that's just the distance between the tips, right? So what I want, let me just change color just for a moment. We'll use the action green here. So basically, I want to know this distance over here. So it's the same thing as knowing the distance between V minus W. Okay, so let's go back to the black. So this is going to be equal to the distance of the vector V minus the vector W. Okay. Any questions on this so far? All right. I'm not exactly sure if I went over this yet in class, but let me just go over it again in the event I didn't. So there's a formula for the dot product. So I'll call it inner product. Okay. So if I take the dot product of two vectors, so we know how to compute the dot product algebraically, right? But there's actually a geometric interpretation of the dot product too. And what you do is you take the length of V and then the length of W, and then you look at the cosine of the angle sort of given by the vectors. So cosine of theta. Okay. All right. So where theta is the angle between V and W. Okay, so this is a very, very famous formula. It gives a geometric way to figure out what the dot product is. If you know about cross products, then you have the sine of the angle, which gives you the cross product. All right, now how do you actually show that this is true? Well, it really just follows from using the law of cosines. So let me review that for you. So just a little trig exercise. So let me draw a picture. So let's say this is the angle between the two vectors. Here's V and here's W. And then here is the vector V minus W. Okay. So the law of cosines is a generalization of the Pythagorean theorem. So what it does is it relates the lengths of each of the sides of this triangle with the cosine of the angle. So this is called the law of cosines. And it says that when I take the length of V minus W, okay, that's going to be equal to the length of V squared. So everything is squared, like the Pythagorean theorem, right? Plus the length of W squared, okay, minus 2 times the length of V, length of W, then the cosine of the angle between the vectors. Okay. Now, you know, when the angle is 90 degrees, what's the cosine equal to? 0. So the last term goes away, right? So the last term, this term here is going to be 0. And so you get the Pythagorean theorem. Okay, so it's just a modification or generalization of Pythagorean. All right, that looks pretty good because look, we have the length of V and length of W cosine pretty much on the last term. So let's just move everything to the other side and then show that the other side is the dot product. So this implies that the length of V times the length of W, the cosine of the angle is equal to the length of V minus W squared minus the length of V squared minus the length of W squared divided by minus 2. Okay, I just did a little bit of algebra and that's what I get. Okay. So in order to show this formula in the box, all I have to do is just do this computation and I'm done. Okay, so let's see what this is equal to. So I get the square root of V1 minus W1 squared plus Vn minus Wn squared minus, okay, so everything is squared. So let me just take the square roots of it. Okay, so I don't need the square roots here, so I can just erase the square roots. Okay, so the length squared is just the square sum of squares. Okay, so I can take this one away too. Okay, let's go back over here. So then I get V1 squared plus V2 squared plus Vn squared minus W1 squared plus Wn squared. This is all over minus 2. Okay, now notice what happens when I FOIL everything out. So I get V1 squared minus 2VW1 plus W1 squared. That's my first term. And then Vn squared minus 2Vn Wn plus Wn squared. Okay, and then I have all this other stuff here, so forth and so on. Okay, all over minus 2. But notice if I take V1 squared, this is going to cancel out with this V1 squared over here. And then the W1 squared is going to also cancel out with another W1 squared over here. Okay, so we can cancel all these terms, all those terms out by the terms in the front and in the back when we sort of FOIL everything out. So ultimately I get minus 2 times V1 W1 V2 W2 plus Vn W1. So I just pull the minus 2 out, minus 2 over here, the minus 2's cancel out, and voila, I get the dot product of Vn W. Okay, so it's not so hard of a calculation. So once you set it up using the law of cosines, then this formula turns out to be fairly straightforward to verify. Okay, any questions on this? Okay, so let's work with this. So here's an example. So these are examples. Okay, so 1. So I'll say W be the vector 3 minus 1, 5. And V be the vector 6 minus 2 and 3. Okay. So the problem is to compute the following. So I want to compute the dot product with V and W. I want to compute the length of V, and I want to compute the length of W also. Okay. So first of all, what is the dot product between V and W? Anyone?
V transpose times W.
Sorry, can you speak up, please?
V transpose times W.
Right. So it's V transpose times W. Okay, so let's just write it out. So V transpose is 6 minus 2, 3 times W is 3 minus 1, 5. Okay, so what is the answer?
— 60.
Let's try it again. 35, very good. So let me go slower and just, make sure everybody understands. So we take 6 times 3, right? Plus -2 times -1 plus 3 times 5. Because I want to understand, that's what we're doing. We're taking the components and we're taking the products of the components, and then we add them together. And so now we just add. So 18 plus 2 plus 15 equals 35. Okay, everyone all right with that? Yes. Okay, good. All right, so now let's do another computation. What about the, what do you got, what about the length? Okay, what's the length of V? What should we do?
7,
Let's,
the square root of each component squared.
right,
Add
okay, so let's do that. Oh, that's right. Okay, so let's just do that. You're right. So 6 squared, okay, plus -2 squared plus 3 quantity squared. Okay, so that's the square root of 36 plus 4 plus 9, square root of 49, very good, and that is 7. Good, okay. And now let's just do the, W. So we just do the same thing. Square root of 3 squared plus -1 squared plus 5 squared. Okay, so that's the square root of 9 plus 1 plus 25. Okay, so this is the square root of 35. Everyone okay with that? All right. So just to show you, so if you take, remember, VW is equal to length of V, length of W, the cosine of the angle between the two. So we get that 35 is equal to 7 times the square root of 35. And that's the cosine of the angle between the two. So the cosine of the angle will just be 35 over 7 times the square root of 35. Okay, if you want to simplify, you can. And then you could actually find the angle between the vectors by taking your cosine. All right. Questions? All right. Okay, so that's the first example. So 2. Okay, so the second problem is find a unit vector in the direction of, oops, come back, of V, which is equal to -6, 4, and 3. Okay. So first of all, I have to say what a unit vector is. So a unit vector is just a vector of length 1. Good. Okay. So unit vector equals a vector of length 1. Okay. So we basically want this to go in the same direction, and we want it to have length 1, right? So I have to look at the vector which is a multiple of this. So consider lambda V. Okay. All right. So I want this to have length 1. Okay. So let's write this out. So this is the square root of lambda squared v1 squared, lambda 2 v2 squared, plus lambda squared vn squared. Okay. So this is the same as lambda times the length of v. Okay. All right, so we want this to be 1. So the scalar is 1 over the length of the vector. So to get a unit vector in the direction of v, I just divide by the length. So we need to consider, so to get, let me just write out explicitly, a unit vector in the direction of v, what do? You take v and you divide by the length. Okay. All right, so let's do this example then. So the length of v, so the length of v here is equal to the square root of 36 plus 16 plus 9. Okay, so I think this is 61. Okay, and so the vector, the unit vector, I'll call it u, is equal to v over the length of v, and that's equal to 1 over the square root of 61 times the vector we started out, minus 643. Okay. All right, any questions on how to find unit vectors in the direction? Again, just divide by the length. Okay, so now I'm going to do one more example. Example number 3. Find the distance between the vector v, which is 1, 0, 2, and w, which is the vector 5, 3, 1. Okay, so I have 2 vectors. So how should I find the distance between the 2?
The distance of the minus W, the distance of W, as I know.
Wait, so I want to, I mean, here's a picture, right? I want to take, yeah, that's exactly what you do. So remember, these 2 vectors, so I want to find the distance between the tip of this and the tip of that. So that's the distance between v minus w, which is the same as distance of w minus v. All right, so let's figure out what v minus w is. Okay. So I just subtract off, you know, the first component from the v. I subtract off the first component of w from the first component of v, right? So what I get? I get minus 4 here. I get minus 3, and then I get, is that a 2? Okay, we'll call it a 2. For all intents and purposes, it doesn't matter. Okay, everybody all right now? We just get the distance here, and we just get the difference. Okay, so now we know how to find the distance between distance of a vector. I just take the square root and I square everything, so it's 16 plus 9 plus 1, and I get the square root of 26. Okay, everyone all right with this? Okay. All right, any questions about these basic operations involving inner product and length. All right. Okay, so now we're going to move on to the concept of orthogonality. That's an L, orthogonality. All right, so whenever you think of orthogonal, you should think perpendicular. All right, so two vectors are orthogonal if basically the angle between the two is 90 degrees. Okay, so it should be, it's almost synonymous to being perpendicular. All right, so recall that the dot product of two vectors is the length of v, length of w times the cosine of the angle between the two. Okay. So when it's when the vectors are perpendicular, the angle between them is 90 degrees. Right? So the theta here is 90 degrees. And so whenever the angle is 90 degrees, that means the cosine is 0. Right? So v and w are orthogonal. If and only if cosine of theta is 0, i.e. theta is equal to like pi over 2. And that's the same if and only if the dot product is equal to 0. Okay. All right, so we should just step back and think about this for a second. If I just gave you two vectors, arbitrary vectors, they could have 1,500 coordinates in them, right? I mean, how would you actually, in practice, figure out whether they're orthogonal or not? Well, this dot product is an incredibly useful tool, right? Because you can just algebraically do that. You just take the product of the coordinates and you sum them up, and if it's equal to 0, it's perpendicular. So the dot product is an extremely useful device. Okay, so this is the definition. So let me just explicitly say this. The definition, V, comma, W are orthogonal if and only if the dot product between the two vectors is 0. Okay, good. So let me make another definition too. This definition isn't quite as important. So, but let V be a subspace of Rn. Okay, and set V perp to be equal to the set of all vectors in Rn such that V times W is equal to 0 for all V and V. And so this is called the orthogonal complement of V. All right, so it's not hard to picture what the orthogonal complement is going to be. So let me draw you a picture. So this is a picture of a three-dimensional space here. Okay. Now let me depict V as a plane. Okay. All right. So what do you think the orthogonal complement looks like? I'm going to look at vectors which are perpendicular to this plane.
The normal vector?
The what?
The normal vector of the plane.
There's a normal vector, yes, but do we take, so I want to look at the collection of vectors which are perpendicular. So I could put them all at the origin, certainly, right? So, and I can also stretch them. So the complement V perp is just a line which is perpendicular to this point. It contains all the vectors on that line. And so one of the things you could prove is that the orthogonal complement is actually a subspace. So V perp is a subspace of also R. Okay. All right. Okay, so let me ask if everything's clear so far. All right, so in the last few minutes, I want to discuss the important concepts of orthogonal projection. Okay, so this will be very important when we do, for example, the Gram-Schmidt orthogonalization process, and also talk about least square solutions. Okay. All right, so let's discuss orthogonal projections. All right. Okay, so the concept is not hard. Let me just sort of draw you a picture. All right, so first of all, let's say I have two vectors. So I'm going to draw one of the vectors on this line here. Let me call this vector u, okay? And then I have another vector, which is not necessarily perpendicular, but it sort of shoots out from here. Let's say that's the origin. And let's call this vector y, all right? So what I want to do is I want to take the tip of y and I want to project it down orthogonally onto u. So the idea is we want to actually form a vector like this, okay? And so I want a vector like that. And so in order to actually write that vector in terms of the component going in the direction of u and actually the perpendicular thing, I actually have to write out what the projection is. Okay, so let me try to use a different color just to capture this idea. Okay, let's use the green again. Okay. So the idea is I want to actually write this vector here, which is alpha times u. Okay. And this vector is going to be equal to z. Okay. So, so what do we want? We want y to be equal to alpha u plus z. Let me change colors again. Sorry about that. Okay. So we want alpha such that the vector y can be sort of decomposed in terms of alpha times u plus the vector z. So the vector z goes in that direction. Okay, does everyone see how we're sort of taking that vector, we're decomposing it times a vector which goes in the direction of u, and then something which is sort of orthogonal to u. Okay? All right, so what we have to do is we have to find a formula for alpha. Okay, so the idea is to find a formula for alpha. Okay, so once we find a formula for alpha, we can actually find what z is. Okay. Okay. So we have, well, what do we know? We know that u is perpendicular to z, right? Okay, so u is orthogonal to z. So that means that U has to be, so that means that Z has to be, has to have inner product, which is 0 with U. So U dot, well, what is Z? Z is going to be equal to Y minus alpha times U. That has to be 0. Okay. All right. So now what you do is use the property about dot products, namely this distributive property. So that means that U dot Y minus alpha times U dot U is 0. Okay. And now you just solve. So U dot Y is equal to alpha times U dot U. Okay. So therefore alpha is U dot Y over U dot U. Okay, so you can actually find this scalar alpha by just taking dot products. That's rather nice. So this is an important formula. Okay. So the orthogonal projection of Y onto U is, and I'm just going to call this Y hat. That's going to be equal to alpha times U, which is equal to U dot Y over U dot U times U. Okay, so Y hat is equal to this vector here. Okay, I'll just let you stare at it for a second. Okay, so basically we're taking this vector U and we're just sort of orthogonally projecting it down. Sorry, we're taking this vector Y and we're orthogonally projecting it down to U, and then we're finding the scalar it takes to actually stretch U to become that vector. Okay, questions? Okay, so we can do an example. Okay, so let Y, yeah, didn't write very well there. Let me try it again. Let Y be the vector 2, 6, and U to be equal to the vector 4, 7. Okay, so this is an R2, all right? So the problem is to express Y as a sum of a vector in the span of U, okay, and a vector orthogonal to U. Okay, so let me just put the picture up. So we have Y over here. So if we find the orthogonal projection is a scalar times U. So certainly it's in the span, okay? And the Z vector is certainly perpendicular to U. So we have all the tools here to sort of answer the problem, right? So we have that Y is equal to Y hat plus Z. Okay, so that's what we have to do. So remember, Y hat is the projection, so it's in the span of U, and Z is perpendicular. All right, so we just compute this out. So Y hat, what's that equal to? Y dot U plus U times U dot U times U. Okay, so what's the inner product of Y and U? Anyone? 14 plus 42, right? No, 8 plus 42. 50. What is u dot u? 16 plus 49. Anyone? 65, yeah. And then u is just, well, u is u. U is just 4 stuff. Okay, so we found that one. Okay, so now to find z, we just subtract, right? So this gets that one, and then z here, you just take y minus y half. Okay, we know what y is, that's 2, 6, minus 50 over 65 times 4 7. 4 over 7. Okay, and then you could actually, do the simplification. Okay, any questions on this? Yes, no. Okay, so let me just briefly say what we're going to do next time. So next time, we're going to talk about orthogonal sets. All right. And we're going to talk about orthonormal sets. And then what we'll do is we'll actually talk about the general projection. Sorry, I'm still going, right? Yes, please don't put your stuff forward. I think I still have like almost 5 minutes left. Okay, so we'll talk about general projections. Okay, great. All right, and then we'll sort of move towards other topics on Monday, and then we have a break, and then we'll go on online. Are there any questions from the people on Zoom? Yes, no? Okay, so we'll stop here, and then we'll continue on Friday. Oh, orthonormal sets. Sorry. Yeah, orthonormal sets. Those are sets where things are orthogonal, but they all have units. All right, good. So before I need to come up and get the come on. Let me shut this down. Okay, stop share.